Okay, so this lecture did not explain how to know whether you incorrectly specify your model. So we're going to perform a specification error test. All right, so in constructing an econometric model, the model should include key variables, so called core variables suggested by theory. In this lecture, we consider several ways in which a model can be deficient, which we label specification errors. Uh, some of the major specification error that a researcher may encounter in practice are, so there are three situation that we consider the model to be misspecified. So the omission of irrelevant variables, inclusion of unnecessary variables, adopting the wrong functional form. So the first one, your omission of irrelevant variable, so meaning that you did not include an important variable in the model. Okay, second one, inclusion of unnecessary variable. So you include what we call that the variable that's not important to explain or to describe or to explain the dependent variable. And then the last one, adopting the wrong functional form. So for example, if the correct model is a double log model or non-linear, other non-linear model, for example, the quadratic model, but you estimate the model using linear model, and then that's what we call as adopting the wrong functional form. Okay, so consider the first case, omission of irrelevant variables. For a variety of reasons, a researcher may omit one or more explanatory variables that should have been included in the model. As an example, consider the following model as the correct model. So let's say this is the correct model. But so in the correct model, we have 2x uh, important or relevant variable to explain y, but instead we estimate this model without x2. So the second regression model exclude the relevant variable x2. So consequences of what we call the excluding the x2, the important variable. So by referring to the given example, the estimated coefficient in the incorrect model are biased. That is, their average or expected value do not coincide with true values. So meaning that the average of the all possible estimate from different sample will not give you the true value of the, I mean, it is not equal to the true value of the parameter. So the error variant estimated from the incorrect model is a biased estimator of the true variance. Okay, so as a result, the usual confidence interval and Havel's testing procedure are unreliable. Second one, inclusion of irrelevant variables. Sometimes researchers include all sorts of variables in the model, whether or not they are theoretically detected. Suppose that the correct model is given by this. So x1 is the relevant variable to explain y, but we add more variable in the model. However, we add the superfluous on the one that's not relevant, variable x2, and estimate this model. Now, the implication or consequences of adding the irrelevant variable in the model, the estimated coefficient from the incorrect model are inefficient. That is, their variances will be generally larger than those of the estimated coefficient from the true or correct model. As a result, the confidence interval based on the standard error of estimated coefficient will be larger than those based on the standard error of the estimated coefficient of the true model. What will happen is that the true coefficient will not be estimated as precisely as as if we had used the correct model. So generally least square estimator are not best linear unbiased estimator. And then the third situation, the third case is the incorrect functional form. So consider the following two specification of the model. So the first one is a linear model. Second one is a double log model. So now the dilemma in choosing between the model is that economic theory is usually not strong enough to tell us the functional form in which the dependent and exponential variables are related. If we choose the wrong functional form, the estimated coefficient may be biased estimate of the true coefficient. So how to detect that we use incorrect specification, model specification? So for the case of unnecessary inclusion of unnecessary variable, then you can just use the walk test that I explained before. Perform hypothesis testing. Perform hypothesis testing whether you perform the test using the t-test for the individual coefficient, or you can perform a joint test using the walk test. So joint test of I mean more than one uh, parameters. So suppose we have the following 4 variables model, so including y. So one dependent variable, 3 independent variables. So if theory says that all 3 x variables determines y, we should keep them in the model, even though after empirical testing we find that the coefficient of one or more of the x variable is not statistically significant. However, sometimes we have control variables in the model without any theoretical support, and we are not sure whether they are really belongs in the model. So so again, so if let's say based on the theory suggests that, for example, x3 is the important determinants of y, then you should include x3 in the model. Although after you estimate it is not significant, and you need to keep the x3 in the model. Okay. However, however, sometimes we have control variable, for example, x3 in the model without any theoretical support, and we are not sure whether they are really belong in the model or not. Okay, so remember that the implication of having irrelevant model, irrelevant variable in a model, that will make your estimate to be inefficient. Okay, inefficient means that less accurate lah, less accurate estimate. So suppose in the model x3 is the control variable, one simple way to find out is estimate the regression and estimate the regression is to find out is to estimate the regression and test the significance of the corresponding estimated coefficient. So under the null hypothesis that beta 3 equal to 0, if we do not reject the null hypothesis, the variable x3 is probably a superfluous variable. If we reject the null hypothesis, the variable probably belong in the model. Okay, so let's say this one, you want to know, you're not sure whether x3 should be included in the model or not, then you just perform hypothesis testing for the individual parameter beta 3 equal to 0 against alternative not equal to 0. So if you do not reject the null hypothesis, then meaning that x3 should be excluded from the model. But if you reject, conclude that beta 3 is not equal to 0, then you should keep x3 in the model. And then, but suppose we are not sure that both x2 and x3 are relevant variables. So in this case, we would like to test the null hypothesis that beta 2, beta 3 equal to 0. So it's joint test, the joint test using the walk test. This can be done easily by the f-test or the walk test. So refer to the my previous explanation on how to perform the walk test for joint hypothesis testing on more than one what we call absolute parameter. Okay, and then to test for omitted variables and incorrect functional form. So this one, previously, the previous explanation, the technique that we use, perform hypothesis testing, in order to know whether we have irrelevant variable, not important variable in the model or not. Okay, and how about if in order to know whether we have excluded important variable from the model, or we use the incorrect functional form? Okay, then we can use reset test. Reset test is a test that can be used to to give us what we call the idea whether the model we use is what we call that incorrectly specified in terms of what we call the exclusion of the important variable, or that we use the incorrect functional form. So either one. So if if the model failed the reset test, then it give indication either that the model we exclude the important variable or relevant variable from the model or what we call that the functional form we use is not the correct one. Okay, let's say we use linear, but the correct one is, for example, a double log model. So to detect the omission of variables and or the choice of inappropriate functional form, Ramsey has developed a general test of model misspecification. Assume that we consider the following model, this one. So the step, so let's say this model, we want to know whether the model is correctly specified or not using the reset test. The step involved in the application of reset reset are as follows. So from the chosen model, obtain the estimated y. You estimate the model and then get the fitted values of y, fitted or predicted values, and then rerun the chosen model by adding powers of fitted values, such as the square of fitted values, or to what we call that fitted value to the power of 3, and etc., to capture the systematic relationship, if any, between the residuals and estimated y. For the given example, let us consider for a model. Okay, so in this case, after you estimate the model, okay, and then you get the fitted values y hat, and then you re-estimate the model, you add the what we call the square of the fitted values. So this one, we include this one in order to know if the square of x, any what we call that square of any of the x is better to be used to explain a dependent variable. Okay. So remember that if you have the model, simple regression model, and then after you estimate, you get y hat, the fitted, this one the fitted values. So if you square the fitted value y hat square, it's just like so that we have this one. So meaning that so when we add this one to the model, the y hat, okay, we rerun the model and we add the square of the y hat. Is just like we want to know if the square of each of the x, square each of the x independent variable in the model, what we call that can explain the model better. Okay, if it is significant, then it can explain the model better. Okay, so why we add the square of what a predicted value instead of the square of x itself? Okay, so imagine that if you have a model that has many x in model, so it is not a good idea. What we call to It's not a good idea to re-estimate the model by adding a square of each of x. Let's say you have 10x, x1, x2, up to x10. Then you need to have, I mean, in the model, when you re-estimate the model, you add x1 square, x2 square, and so on. Then you have so many additional variables, meaning that we lose a lot of degree of freedom. Okay, remember that degree of freedom n minus k minus 1. So we have too many k in the model, then it is not a good idea to add the square of what we call that each of x in the model. So instead, I mean this technique is suggest that instead of adding square of each of x, you just add the square of the fitted value of y. Okay, this one, so that because we know that uh, the fitted value of y, it is equal to an equation that has that involve the square of x. Okay, and then you also can include the to the power of 3 of the fitted value y hat, so that we also want to know whether this the power what we call it, the x to the power of 3, any x to the power of 3 of x, what we call that can explain the dependent variable a bit better. Okay, so if you use the default setting is that it will only include one terms of the fitted values. One term means that only one. This one y hat square. If you put two, then we include both this one y hat square and to the power of 3 of the fitted value. Then we can use the f-test using this formula. I mean, you compute this based on this formula. The r square of the new model, this one, minus r square of the original model. Okay, divide number of new regressor in this one, in the second model, the number of additional what we call that independent variable. So in this case, for this example, we have 2 lah, and then divide by y minus r square of the new model, and then divide by number of parameters in the new model, number of parameters. So including the what we call that slope coefficient for original model and then the intercept. So if the computed f value is statistically significant at a chosen level of significance, we can conclude that the initial model is misspecified. So if we reject the null hypothesis and conclude that the model is misspecified, it is either we haven't included an important or relevant variable in the model, or we have used the incorrect functional form. So consider example. So we have data on US expenditure on important goods, okay, and personal disposable income X. Okay, let's say initially we just used a simple regression Y regress against X, and now we want to know whether the model is correctly specified or not based on the reset test. So this is the data. So estimate the model first. So Y space C space X. Okay, so this one, if you estimate using eViews, then you can easily perform the reset test. You go to view, stability, Ramsey reset test. So if number of fitted terms equal to 1, it means that we just include the fitted value square, the y hat square. But if you put equal to 2, then meaning that we put both, y hat square and y hat to the power of 3. Okay, so let's say we perform the same test that given or explained in the H0. Okay, so we put 2, so you get this one. Okay, so F test ST 8.77 and then p value less than 5% if 5% significant level. So you reject, conclude that the model is misspecified. So as for solution, so you need to explore, you need to consider whether you need to find first possible solution. You need to try to find other important variable to be included in the model, or you also consider that the possibility that the model is incorrectly specified. I mean, use the incorrect functional form. Maybe the usual linear model here, but the correct model is quadratic regression model, or the what we call the double log model and so on. Okay, now how we produce this value? If you want to use the formula given in the H0, what you need to do, you need to estimate the model, original model. So you go to view, you get your y hat view, actual fitted residual. So this is your fitted value y hat. Y hat is for what is the value of predicted value of y for each value of x. Okay, so if you copy this one and then you go to this one, object, new object, series. Okay, so we create a new variable named y hat. So we store the values we produced just now, the y hat. Okay, and then, okay, so when we estimate this one, it gives us the R square, this one, the R square of the original model. Okay, so to get R square for the new model, okay, re-estimate. So you put y hat square, and then y hat to the power of 3. Okay, so this is our R square of the new model, 0.9695. Okay, then you can compute using the formula given before. So for degree of freedom 2 and 16, 5% significant level, the critical value, you refer to the F table, it is 3.63. Since the computed F value is greater than the critical value, we draw a conclusion that the model is misspecified. And then since the data is time series, as for remedy, we could consider to include the trend variable as additional explanatory variable. And then perhaps we should consider alternative functional form by adding a square trend variable as well. So you need to explore lah. So what is the possible solution? Okay. So for example, this one just now, if let's say because it's time series data, maybe you can consider to include a time trend variable. Okay, so time trend variable. So this one add trend plus one, you get this one. So you perform the reset test. Okay, let's say you just include the most of the time the inclusion of y hat square is already sufficient to capture for the possible non-linearity in the what we call that uh, in the model, in the what we call the relationship between y and all the independent variables. But you also can include, if you put 2, then you include the y hat to the power of 3 as well, so that we can use that to detect if the power of 3 of any of x, okay, what we call that, can explain the model better. Okay, but basically most of the time, I mean the y hat, the fitted value of the y hat, sorry, the square of the y hat is already sufficient. Okay, it's already is sufficient for us to what we call that, to know whether the non-linear model is better to be used as compared to the linear model. So okay, let's say for this one, let's say we try to add trend. So this is, although it is still smaller than 5%, but I mean, if you compare to the previous one, it is much better. Okay, so at least for 1%, if I mean, let's say if you use a 1% significant level, um, then you can conclude that the model is correctly specified. Okay, but if you perform the test again, let's say you include 2. Okay, this is much better, greater than 0.05. Um, but remember that when we include both, okay, when we include both the fitted value of y, sorry, the square of the y hat and to the power of 3 of the y hat, then we include both, although it allows us to know whether, or to detect whether the what we call that to the power of 3 of x uh, able to explain y better. But because we add 2 terms, okay, so it is, the result is, it is less reliable as compared to when we only, when if we only include 1 terms of the fitted values. Okay, but if we include 1 terms of the fitted value, then we only able to what we call that, we just test whether the square of x, okay, explain dependent variable better than what we call without the square of x. Okay, so this one, or maybe you can consider what we call that different functional form. Maybe it produce better model. All right, so that's how we perform reset test in order to know whether we. So when we reject the null hypothesis, there are 2 possible reason. Okay, the first possible reason is that we haven't included an important variable in the model. Second possible reason that we use, I mean, possible that we use, the possible reason that we have used the incorrect functional form of the model.